Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 6.3, which introduced you guys to the method of cylindrical shells. Since the method of disc and washers and the method of cylindrical shells are our two main methods for handling solids of revolution, we're really going to treat this video as sort of a summary of both methods and seeing how to use both of these on a variety of different examples. So before we get into those examples, I'd like to just give a quick summary of these two methods that we've developed over the past couple videos, talk about their important formulas, and talk about some different notes and comments about each. And then we'll try several examples actually using all this sort of information together. So, in terms of solids of revolution, which is the sort of concept we've been doing for these last two sections, the main idea has been that if you take an area, so an area of some region in two dimensions, and you revolve that area around some axis, then revolving that two-dimensional area creates a three-dimensional shape that has volume. And we've been trying to figure out how to use integration to actually understand the volume of the resulting solid. So far, we've come up with two methods, and these are the two methods that are going to be for our class, which is the method of discs and washers and the method of cylindrical shells. For each of these, there's sort of an important general formula, so I'd like to talk about those first, and then we'll move on from there. So, for the method of discs and washers, which even though it's called discs and washers, it's really, you can just think about it as the method of washers, because as we talked about, a disc is really just a washer with an inner radius of 0. So really, you could just abbreviate this as the method of washers. The general formula for the method of discs and washers is the integral of pi times the outer radius squared minus pi times the inner radius squared. And remember that the sort of piece that is creating this, right, again, the concept is we're integrating an area to create a volume. The area of that sort of piece is a washer or donut shape, where what you're doing is you're taking the area of that outer radius, so that would be everything in here, and then you're removing the area of the inner piece and stuff in here, so you end up with just the area in between. And then once you take that area and you accumulate that area all together over whatever interval, that creates the volume. So that's the sort of method of discs and washers there, and that's the sort of general formula. For the method of cylindrical shells, it's a little bit different how we're composing our three-dimensional shape. The general formula is 2 pi times the radius times the height, which is coming from the surface area formula for a cylindrical shell. So in here, the sort of pieces that we're looking at are going to be these shell components, where these shells, again, they could be on their side as well, so they could look something like this instead. But these shell components are actually hollow, so we're just treating them as a surface area, so just the shell, and then we're stacking those shells inside of each other to create the three-dimensional shape. So here, the area that we're talking about is the area of that washer, which is why we have that pi outer radius squared minus pi inner radius squared. Whereas here, the area we're really talking about is the surface area on the outside of that cylindrical shell, which is 2 pi RH. Either way, in both of these formulas, we're integrating an area to create a volume. So, doesn't matter if you're working with respect to x or with respect to y, these two formulas are always the formulas that you'll be using for each method. The next thing that we sort of want to summarize is determining the variable of integration. So each method has a specific variable of integration based on the type of axis you're revolving around. So you guys can use this table to sort of summarize that. The way you should sort of read this table is we've got two different types of axis of revolutions that we've been discussing. Horizontal axes of revolution, that means things that are parallel to the x-axis, and vertical axes of revolution, so that means things that are parallel to the y-axis. When working with discs and washers, if you have a horizontal axis of revolution, you'll be working dx, whereas if you have a vertical axis of revolution, you will be working dy. For cylindrical shells, that's flipped. So for cylindrical shells, if you have a horizontal axis of revolution, you work dy, and if you have cylindrical shells and you're revolving around a vertical axis, you work dx. Notice that what this basically means is that in any given example or any given problem, you only have a single axis of revolution. You always have either a horizontal axis or a vertical axis. And what this table is basically telling you is that if you have a horizontal axis, then you have one method that lets you work dx and one method that lets you work dy. If you have a vertical axis of revolution, you have one method that lets you work dy and one that lets you work dx. So regardless of what type of axis of revolution you can always choose a method so that you can work with the variable that you want to work with. Now, in a lot of the examples we're going to be doing in this video, we're going to force ourselves to do every problem twice, once with respect to x and once with respect to y, to get really comfortable working with both. But that's the main idea here, is because we wanted to be able to work with both variables, that's why we really took the time to develop two methods. So that regardless of the axis of revolution, we always have a method that lets us work dx and one that lets us work dy. In terms of visualizing, which is strongly recommended anytime you're trying to do this, there's a few tricks for visualizing what's creating your discrete washer or your cylindrical shell. So, something we'll be using a lot in today's video as we do our examples is whenever you're working with discs and washers, the best way to sort of visualize that is you draw perpendicular from your axis to the region. So in other words, you start from your axis of revolution, draw perpendicular to that axis all the way to the region. The first time you intersect with the region is going to be your inner radius, whereas the second intersection is going to give you the outer radius. So this gives you a nice way of sort of understanding visually how we create those discs and washers. For cylindrical shells, the drawing is a bit different. For cylindrical shells, what you want to do is you want to draw parallel to the axis inside the region. So instead of drawing from the axis and going out to the region, for cylindrical shells, you draw parallel to your axis and you draw your lines inside the region to begin with. And as we start to do examples, we'll see why these two visual tricks basically show us how we always get disc washers or cylindrical shells. Finally, as one sort of computational note, which I think I've mentioned in several of the previous examples, the axis of revolution, whatever that axis of revolution is, will always appear in the radius part of the formula. Radius is really a sort of more general definition of radius, is measuring the distance to the axis of revolution. So the formula for the axis of revolution, if it's a non-standard axis, something like, y equals 5 or x equals -2, that's always going to appear in the radius part of the formula. Now, when I say radius part of the formula, obviously in discs and washers, everything is a radius part of the formula, but in cylindrical shells, the radius part of the formula is right here. So in other words, you can sort of think that the axis of revolution is never going to appear in the height component of this method of cylindrical shells. Okay, so this is our sort of summary of all this sort of information. We're going to look at a bunch of examples now, running through using, in every one of the examples, both methods so that we can build one integral that's with respect to x and one with respect to y. And we'll try to use all of the components in this summary to make that a bit easier. So let's go ahead and start taking a look at those examples. So, for our first example, we're going to consider the volume of the solid created by revolving the area between y equals the square root of 8x and y equals x squared around the axis x equals 3. So, this is going to be a little different than some of the previous ones we've done because we actually have the area between two curves and we have a non-standard axis, x equals 3. So what we want to do is we, of course, want to begin by trying to get a sketch. Notice, though, that since no boundaries were given for these curves, we pretty much know that we're going to need to find points of intersection. So it might be a good idea to start with that. So let's do our points of intersection here. So for the points of intersection, we can take the square root of 8x and set it equal to x squared. I suppose we can square both sides and get 8x equals x to the fourth. That's 0 equals x to the fourth minus 8x. And that gives us 0, factor out an x cubed minus 8. So it looks like we get x equals 0, and we get x cubed minus 8 equals 0. And solving that, pretty easy to see that that's going to be x equals 2. Those are, of course, the x values of the points of intersection. So let's see what those actual coordinates would be. Plugging in 0 into either of these is going to give us the intersection 0, 0. And plugging in 2 into either of these, here would be 16 squared root of 16 is 4. 2 squared is also 4. So we have the point 2, 4. So that gives us a better sense of where we should be sort of drawing this. So let's go ahead and draw in our axes. Keep in mind that since our axis of revolution is x equals 3, we also need to make sure that that's included in our graph. So we'll go 1, 2, 3. There's our axis of revolution, x equals 3. Now let's draw in our curves. I guess we also need 1, 2, 3, 4. So probably drawing in x squared is a little easier because we're pretty comfortable with that one. That goes 0, 0, 1, 1, and then 2, 4. So there's that sort of standard parabolic shape. And then square root of 8x, we know square root of x in general sort of looks like that. Square root of 8x is just going to be a little faster than that, but we do know that it's going to intersect there. So there we go. There's the sort of region, and of course the stuff that we want is the stuff in between these. So we're sort of shading in this stuff here. Okay, if we want, we can draw a sort of rough approximation of the mirror image. So it looks like it would be there, 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 and looks like it should have a piece like that and a piece like that. So that's going to be sort of the mirror image piece. And like I said, in some of the past ones, I actually took the time to draw this and this component out. I'm going to start skipping that because, again, I think that makes the diagram messier than necessary. So I recommend just getting the region and the mirror image of the region, and then, of course, actually drawing in the sort of the thing that's creating either your disc and washer or your shell. Okay, so at this point, we haven't done anything related to sort of the actually coming up with a volume or a method. We're just trying to get a sense of the sort of drawing here. And again, also might be a good idea just to label those corners 0, 0, and of course this component here was 2, 4. Okay, so let's go ahead and start with A here. So we have a vertical axis of revolution, and we want to build, at least in A, an integral with respect to x. Remember, WRT just means with respect to. So we have a vertical axis of revolution, and we want to work with respect to x. If we're comfortable, we can probably know which method that is immediately, or we can just go back to our table here. We've got a vertical axis of revolution. We want to work dx, so that shows us that we're going to have to begin by working with cylindrical shells, our newer method. So, since we have a vertical axis, this tells us that dx will be, or we can maybe phrase it this way, which would be more normal. We can say cylindrical shells will be dx. So, we know that if we use the method of cylindrical shells, we'll be allowed to work dx. All right, so let's go ahead and draw in that typical piece for cylindrical shells. If we go back to our summary here, remember we said that for cylindrical shells, you want to draw parallel to your axis inside your region. So we want to take a particular value. Notice that since we know we're working dx, and since we're working parallel to this axis, that means we're drawing a vertical line, which is an x value. We draw something sort of typical in there, maybe something like that. There we go. We'll zoom in a little bit so we can sort of see. It's a little messy, apologize. Let's remove that. Okay, there we go. Okay, and then of course that would reflect somewhere over here. Again, it's just arbitrary, so it doesn't matter which one you pick. And then you can actually see I would draw in the typical shell. There we go. So there's our shell there, and if you want, you can even fill in those portions there. So there's the shell shape that we are sort of going to be stacking together inside of one another to build our overall shape. You can also see that right here, this distance here, that's going to be your radius, and this distance here, that's going to be your height. Okay, so let's go ahead and start to set this up. We know that in general, cylindrical shells is going to be the integral of 2 pi rh. So in our case, it's going to be the integral. We know we're working dx here, and we can sort of confirm that visually here by recognizing that we have these vertical lines. Where can we choose these? Well, we could have chosen here, 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 here. It's anywhere from x being 0 to x being 2. Notice that corresponds to the bounds in terms of x of our region. So we know that our integral is going to be from 0 to 2, 2 pi. Let's think about our radius. So our radius is measuring from our selection to this axis. Remember, the radius component always has to involve the axis, which is 3. Notice our x value, because it's between 0 and 2, is always going to be less than 3. So this radius should either be written as like x minus 3 or 3 minus x. X minus 3 is always going to yield a negative number, which doesn't make sense for a radius. So we know that the radius should be 3 minus x. And that makes sense because our choice of x is going to be smaller than 3. So to measure from here to here, we would start with 3 and then subtract our choice of x. 3 minus x is our component for our radius. Notice, as stated back in this note here, The axis of revolution always appears in the radius part of the formula. We're on the radius part of the formula right here, and there is the axis of revolution, x equals 3. What about the height? Well, if we look, the height is between these two curves. We know that the square root function is on top, so we would use that as the top function. Square root 8x minus the bottom function, which is that x squared, so minus x squared dx. So there we go. There's an expression for the volume of this shape up here based on cylindrical shells, which guarantees that we'll be working dx there. We're not going to go through and evaluate this. If you did need to evaluate it, the first thing you would need to do is multiply these things out, and then hopefully you could get away with just power rules from there. You would have to be a little careful with that square root of 8x, probably treat that as a u substitution. But there we go. We've handled part A of this. Okay, now we'd like to go back and attempt part B. To do that, I'm going to redraw real quick because it would get pretty messy to take all of this stuff and try to draw another thing on there. So let's give ourselves a sort of fresh page here just with the question and everything. We already know what the diagram is going to look like, so we should be able to sketch it relatively quickly. We know we've got 1, 2, 3, 5, something like that. There's our axis of revolution at x equals 3. We got 1, 2, 3, 4. There's our quadratic component, y equals x squared. And then there was this guy. Then this came over to here and down to here. So there's our components. I'll zoom in a little bit. Remember, our region is this stuff in here. Okay. So, and of course, we're going around this axis here, and corners of this region, 0, 0, and 2, 4. Okay, perfect. So, let's go ahead then and think about how we're going to build an integral with respect to y. Well, we have a vertical axis of revolution. So, if we go back and we check our little table here, vertical axis of revolution, we want to work dy. That tells us we'll be using disks and washers. Notice this is always going to be the case. If you're working on a single problem, which has a single axis of revolution, which they always are going to have just one axis of revolution, then one of the methods will be dx and the other will be dy. You're never going to use the same method twice because they always have a different variable of integration here. So to do this dy, we're going to have to work disks and washers. So for B here, we want to work with respect to y. So a vertical axis here, right, which is what we had. This tells us then that we want to use disks and washers. It will be dy. Okay, so disks and washers will be the method that allows us to work with respect to y. All right, now to do this, we need to remember sort of the general formula is going to be the integral of pi times that sort of outer radius squared minus pi times that inner radius squared. Okay, since we know we're going to be working with respect to y, before we get too far in, it is probably a good idea to go back and think about each of these functions in terms of y. So we can just do that sort of maybe down here. We had y equals root 8x, which means y squared equals 8x. So we should probably think about that one as y squared over 8. And of course, we also had y equals x squared. So we can think about that as x equals the square root of y. Technically, this is a limited inverse, right? It really should be plus or minus square root of y. But of course, we know we're working in the component where where x and y are always positive. So we're safe in using the positive root there. So those are going to be our two inverse functions. This one is the square root originally, and this one was the quadratic originally. So it'll be that component there. All right. Let's go ahead and draw in what's creating our disks and washer. So if we go back and we check visually for disks and washers, what you want to do is you want to draw a perpendicular from the axis to the region. The first intersection is the inner radius, second intersection is the outer radius. So let's find ourselves on our axis here. Just choose a random value. Notice that the random value would be a random y value, right? Because we could choose anywhere up here or down here. Then we draw perpendicular to our axis, so we're drawing horizontally to our region. So here we go. there's our first intersection. And then, of course, that's going to be revolved to here. That's going to create that inner radius. And then we would continue out to here. That'll revolve to there. And this guy, this guy will create that outer radius. So you can see the first intersection is going to be the inner radius. Second intersection is going to be the outer radius. So let's see if we can say what those are going to look like. So the integral first, what are going to be our boundaries? Well, we could have made this selection anywhere from down here all the way up to here. What were those in terms of y? Well, it was from 0 to 4 in terms of y. So 0 to 4, pi. Outer radius is measuring from here out to there. This curve here, we said, was the square root, so it's that y squared minus 8. Now, it has to be measured to this. This guy is going to be definitely larger. X equals 3, right, is further out to the right here. So we would be measuring from 3 back to this. So we should have that as 3 minus y squared over 8 squared. If you're ever unsure about whether or not it should be 3 minus this or y squared over 8 minus 3, remember, you can always just check. Choose a random value between 0 and 4. Say your favorite value is 1. If you plug in 1 for y, you'd get 3 minus 1/8, which gives you a positive radius. Radii have to be positive. If you accidentally wrote y squared over 8 minus 3 and you plugged in 1, you would get a negative radius. You knew you had it backwards. Notice we also knew that 3 had to show up because axis of revolution always has to show up in the radius components. Okay, inner radius now, so minus pi. The inner radius is going from our axis to the closer one, which was originally y equals x squared, but we're thinking about it as square root of y. So similar structure, it's going to be 3 minus the square root of y squared. And of course, all that is going to be dy. If you took the time to actually evaluate this one, which would be pretty messy because you'd actually have to FOIL these components out and then integrate everything, whatever you found from actually integrating this would exactly match what you found from integrating this. Because again, even though they're with respect to different variables, they're still measuring the same volume. So there we go. There's our first example of going through and building two integrals that match, that evaluate the same area, one with respect to x, one with respect to y. Okay, let's go ahead and take a look at another example here. So, for our next example, similar idea, we're just going to do the same thing. We're trying to write down two separate integrals, one with respect to x, one with respect to y, but we've got a slightly different region here. So we're going to consider the volume of the solid created by revolving the area between y equals sine x, y equals 1, and the y-axis around the axis y equals negative 1. So let's start again before we even worry about this stuff, just getting a good drawing of the region here. So there we go. We'll have to give ourselves a little bit more space because our axis is negative. So let's make sure. There we go. So we want to be drawing y equals sine x. So let's go ahead. There's y equals sine x. And well, let's draw on our y equals 1 first. There's y equals 1. And the y equals sine x, so we'd have something that looks like that. Of course, it'll hit its peak there. If we were going to continue drawing it, it would come back down by pi, and then, of course, it would keep oscillating. But we just want that portion. And our region, because it's supposed to involve the y-axis, y equals 1, and that sine of x curve has got to be this stuff in there. So we can see that our region is going to be this stuff. Notice it's a little bit of a different region than we would normally expect because normally we're used to stuff under the curve, but this stuff is sort of trapped between the y-axis and our curve. We can also label those corners. Obviously, this here is 0, 0. Where does sine of x run into that y equals 1? I mean, I suppose we could set up the equation, but we should know that that's going to be at pi over 2, comma 1. And of course, that right there is 0, 1. And then that equation is y equals sine x. Okay, and then let's put our axis of revolution, which is negative 1. That's going to be down here. So there's y equals -1, and we're revolving around that. So this time we have a horizontal axis as opposed to the vertical axis in the previous problem. Okay, so let's go ahead then and take a look at what's going to happen with this. If we want, we can go ahead and construct this sort of mirror image. So there'll be that point there, and then that point there, and this point, and I guess we'll have something that looks like that. Nope. Concavity the other way. My bad. Let's just go back. There we go. Concavity like that. There we go. And there's our area. Okay, so there's our mirror image down there. So this is going to be our sort of region that we're going to be working with. And again, we're going to skip the point of sort of drawing in the actual 3D component of it. We're just going to make sure that we have our region and its mirror image so we can draw in the sort of typical disc and washer, the typical shell here. Okay, so first thing we want to try to do is come up with a way of doing this with respect to x. So for A here, we want to work with respect to x. So since we have a horizontal axis, to work with respect to x, we need to use discs and washers. So for horizontal axis, discs and washers gives us dx here. So if we work with discs and washers, we will be able to work dx. So let's go ahead and write out the general formula then. So it's going to be v the integral pi that outer radius squared minus pi the inner radius squared. All right, so let's go ahead and draw a typical disc or washer in this case. So since we're working dx, right, we want to draw vertical lines, which makes sense because what do we draw for disc and washers? Well, we start from our axis and draw to our region. So here we go. We're sort of coming along like that. Okay. We run into our axis there, and then if we continue, that'll be sort of, once we revolve that, that's going to give us our inner radius, and then we draw a little further out to there. That's going to give us our outer radius. And if we did that over here, we'd have the same sort of thing. If we did it over here, we'd have the same sort of thing. So that's going to be what's going to happen on the entirety of the interval. Okay, so let's go ahead and write out what that's going to look like then. So that looks like that would hold from x equals 0 all the way up to that x equals pi over 2. So those are going to be our bounds in terms of x. So 0 to pi over 2, pi. What is our outer radius? Well, the outer radius is from here all the way up to here. The equation up here, this was y equals 1, and we're measuring to -1. So if you want, I mean, you could just calculate it and realize that that's always 2, but if you like to write it as an actual difference, it would be 1 minus -1 squared. Why do I like this better? Well, because that minus -1 there shows us the axis of revolution inside the radius formula, which we know always has to be the case. So if you write it as that difference rather than simplifying, you can actually see that. So whenever you're just trying to set up the integral, you guys don't need to worry about simplifying. You just want to write it as you would actually construct it so that it's actually easier to see where the pieces are coming from. Then minus pi, the inner radius, well, that's measuring from here down, which of course is our function being measured to -1. So we would have sine of x, and we're allowed to say sine of x because we're working with respect to x, and then minus -1, and then all squared, and then dx. So there we go. That would give us an expression for calculating the volume of this solid using x as our variable of integration, and because we wanted to use x as our variable of integration, we had to use discs and washers here. So there we go. All right, let's wrap this up with doing this one more time with respect to y. So we'll give ourselves sort of one more page, redraw real quick, and work with respect to y. Since we know we've already used discs and washers, with respect to y is going to have to be cylindrical shells. So let's go ahead and do that. Give ourselves another page here. All right, quick redraw of our region. So we've got that, we got our sine curve there. There we go. Our region is this stuff in here, as we said. Okay. We know that right there is pi over 2, 1. We knew that this thing here was 0, 1. We knew that this guy here was 0, 0. And we had this down here, which is y equals -1. Okay. Mirror image ended up being here and here. And then we also had our point here. And there's our sort of mirror image piece there. Again, doesn't need to be perfect. Okay. So for B, we wanted to do this with respect to y. So since it's a vertical axis, cylindrical shells will be dy. So that means our general formula is going to be the integral of 2 pi rh. Let's go ahead and actually draw that in. How do you draw in shells? Well, you want to draw parallel to your axis inside your region. So a typical shell here would be, maybe I pick something like that, come across to there, that reflects to here, come across to there, draw that in. Notice that that does create a shell, because since it's parallel to the axis, that part comes down here, that creates that shell shape. Now in this case, again, the shell is on its side because we're going around a horizontal axis, but that's totally fine. This is the height of your shell, and of course this distance here is the radius of your shell. Okay, let's go ahead and determine the bounds here. So we'll need to integrate. Bounds are going to be with respect to y. We could have made this choice anywhere from 0 up to 1, which again corresponds to the y coordinates of those corners there. So we have the integral from 0 to 1, 2 pi. Now we need the radius. Radius is based on our choice of y, and then measured down to this y equals -1. So radius here should be y minus -1. If you want, you can also just confirm that makes sense. If I had picked up here, notice that the radius would be 2, which comes from 1 minus -1. If I had chosen here, then my radius would only be 1, which would come from 0 minus -1. Anything in between makes sense to have y minus -1. Once again, axis of revolution always shows up in the radius component. What about the height? Well, the height is going to be measuring from here to here. It's going to be that curve, sine of x. Should we write in sine of x here? Well, of course not, because that's in terms of x. So we'll need to invert real quick. Of course, it's not bad to do that. Y equals sine x. That means x is arc sine of y. Very risky to use an inverse trig function because we know that's a limited inverse. That only is an inverse on that -1 to 1. But of course, that's exactly where we are. We're just in that first portion, first quadrant really, of sine. So we're all safe in using that inverse. And that's exactly what we should use as the height there. Arc sine of y, dy. Okay, so there we go. There's our volume formula for this in terms of y. Once again, if you computationally went through and did this, this would be a pretty tough integral because we've never really talked about integrating arc sine. But if you were able to compute this, you would get exactly the same thing as if you went through and you computed this. Now, currently, both of these integrals would be pretty challenging because if you went ahead and you FOILed this out, at some point you would end up with a sine squared, which is, again, not something that we've covered yet in terms of how to integrate. Eventually, though, we will learn how to handle powers of trigonometric functions for integration. That's why, though, right now, we're more focused on setting up but not evaluating these integrals. Okay, so that's going to do it for the examples for this video. We're going to wrap up all of section 6.2 and 6.3 in one final video after this, where we're going to take a look at one region being revolved around 4 different axes of revolution and seeing how that impacts the formula each time. So we'll have one more video summarizing 6.2 and 6.3 together.